Good afternoon, first of all, of course. Well, I'm in charge in FCC of something we call special works department. Okay, and we try to do.
Excuse me. Perhaps I can make a general introduction first, okay, so that they know a little bit more about you. So I think it's a great pleasure for us and a great honor to have a distinguished speaker here today with us. So José Martínez Salcedo is one of the leading designers in structures, and of course with a special emphasis on steelwork and steel structures, because this is a master on steel structures. And I would like to say a few words about him, because he's the director of special projects at the largest Spanish construction company, FCC, since 2001. And I will only mention a few of the works where he has been involved. Of course, probably most of you have already traveled from Barajas, from the new terminal, very nice terminal with the roof and the facade, the roof of the Caja Mágica in Madrid, the bullfight arena in Madrid, the roof of the stadium of Español, the roof of the Velodrome in Palma de Mallorca, the new roof for the Bernabeu Stadium are just a few of the large span structures that he designed. Also significant work in bridges, the basculating bridges in Barcelona, which is a world record span in basculating bridge. Tarragona and Sevilla, and many composite and truss bridges, arch bridges, PUB, that makes the border between Portugal and Spain. He's the author of 2 reference books and 3 papers. So I will not continue, because otherwise there will be 2 presentations. So the conference is on recent applications of high-strength steels, S460 and S690 at FCC construction. You have the floor. Thank you very much.
Thank you. Okay. Well, this, as he has mentioned, we're not going to talk about this today, because there's some 420 in Barajas, but not too much. Okay. Systems, floating, lifting. Okay, but that's not what we're going to talk today. Is about the high-strength steel. Well, as you can imagine, the word itself has changed a long time. Now, more or less, we could agree to call high-strength steel something that's bigger than 355. But we also need to have, let's say, to be able to. We'll talk about mainly about 460, 690, and I'll try to mention something, but that doesn't mean we have used it. We are trying to use it, but not as something that's weldable, 960, okay? But I think we should, I mean, from our point of view, that we have to afterwards, after designing, we have to do the construction of the system. It's very important to have actually confidence that the things are going to work. So we cannot get into something, into some material in which we have, let's say, any doubt about how it will be working. So we need also, besides the hygiene, the high yield of the material, we have to have a better toughness, so we can avoid brittle failure, and we have to have an improved weldability to avoid cold cracking. That's why I'm going to talk at the end about 960. But never as something, at least from our point of view, as something weldable, at least up to the moment. weldable with the normal things. Okay. At least I wanted to tell you, of course, that we can remember that up to more or less, I don't know, I'm not very good at what date. I mean, more or less on 2005, in the Euro code, we were only got up to 460. And there was some supplementary rules that talk about measure high strength steel. Later on, in part 112, there was we got up to 600 because well it says 700, but 600. But there was a clear difference between, let's say, we'll talk about this later, how these steels are produced, and so how they are going to, how we are going to be able to weld and to work with them. And of course, there was a problem because up to 460, let's say more or less, the rules, the old rules of Eurocode, let's say, were good up to 460. Because there was a clear difference between the yield strength and the putting strength, so you could use plastic calculations. And now, since you get 690, the Eurocode has to start saying, okay, if you're going to do plastic calculation of the section, okay, you can use up to 690. If you're going to do plastic calculation of the structure itself, then you have to only be able to use up to 460. And that's, let's go on. And this is how it would be more or less in 2018. In 2018, already in the normal part, in part 1 of Eurocode, it's 690 has been included. I mean, instead of being in a special part, it has been included in the normal part. And now, at some point, they have said that the 960 would be included in part 12. But it's Kuhlmann, I mean, the maximum person responsible of Eurocode 951. I mean, they have said that that 960 can wait a little bit to be included in Eurocode. Okay. But I understand that this is mainly because, as we will go on talking about this, it's really not a steel, because I understand that Eurocode is for steels and for structures in which the main fabrication process is welding. You have big structures with big plates, and you are using mainly welding. Of course, then you can do bolting on site and all that. You'll see it, of course. But the main fabrication process is to weld. And in 960, we will see that there's still a big problem. So they say, okay, let's wait a little bit. Even for 690, there are still some issues, okay, that we have to be, I understand. I mean, we are very careful. We are trying to be very careful with that. We only work with very good workshops. We do a lot of testing. We even do the testing with the material from the supplier that we're going to use. I mean, we don't buy simply 690 from anyone. I mean, with this, I have tried to tell you that things are, of course, trying to include more steels, but we have to be careful. I understand that we have used up to now 460, 420 in some moment, but I think 420 is it's dead because it's very near 360, 460, 690. We have used it a lot, and we'll see in some of the roof of Bernabeu, we have used more than 3,000 tons, but with a lot of care, of course. And for 960, we have proposed to use it, but without welding. We'll go on to this afterwards. I mean, we have proposed to use it, but not welding. Okay, we are not going to talk about the fracture toughness. That's okay. It's very important because you have to, in the selection of the material, we could say that the yield strength is only the name, but we have to have the surnames. We have to have the quality, how at which temperature, but we cannot talk about everything because we don't have any understanding time. Of course, we have tables in which we can do this selection, or we can go back to fracture mechanics and look at the details in which we need to establish what quality, what subgrade of the material we really need. All these materials, this has also changed from time. At least from my point of view. I mean, when we were younger, the different qualities of steel were in different standards. These are old standards. And now, to make the people understand that all the steels are, say, taken from the same place, the same as in calculations, we have tried to use them all in Eurocode. Now they have placed all the steels in the standard, the famous standard 2025. Okay, but of course there are very big differences because the first ones are the ones we have used all the time from a long time ago. I mean they are raw steel with no alloy, fine grain. This is the normal ones. In the thermomechanical ones are in the number 4. In number 4 are the thermomechanical. We will see that the 460, we could say, is the thermomechanical one. If we have to be, let's say, simple, we would say that up to 355, we would be in the first standards, in the 2 first. In the number 4, we have the thermomechanical one. The thermomechanical one is the 460. We'll go back to this, but we know that in the thermomechanical, we are saying that the properties of the steel, we are not gaining it simply by alloying, we are gaining by a controlled process in the fabrication with rolling, with deformation, and rolling and temperature, the 2 things. And the 690 comes from this standard, the 6th one. Okay. In this one, the steels are, as the name, as you see there, quenched and tempered. Okay. Here we get the properties of the steel that we gain are obtained by, as you know, even from TV, it's a process of putting a sword into water, and you get a very and then we have to quench it a little bit because the properties will be too brittle. But I mean, we are getting all the properties, main properties, are gained by a thermal process. This has to be very clearly taken into account because afterwards, if we are going to weld the steel, we know that we can affect all these properties. Okay. One of the main things I want to talk about during this talk is how how the steels are made in relation with the difficulties and with the care we have to take when we are welding them. Okay, there are very big differences. That's what we should not forget about. 355, it's obtained by alloying, the same or less. It's not always the same. There are some. The thermomechanical ones are in the middle, we can say, and here we have the ones with quenched and tempered. Okay. Well, here you can see. I don't know. Here you can see. It's in 6, in the 4, in number 3 already there are already some 460, but the most parts of the 460 that we can buy are already in the number 4. Okay, in the standard number. Okay, thermomechanical. They are not obtained by simply by alone. Okay. Well, this is as low, normalized, you put the temperature up, you let it slow down quickly, or a thermomechanical process, or the quenching, as I mentioned. Of course, the composition. Why are thermomechanical steels so, people from the companies, from the providers, trying to sell them? Because you need, it's more easier to weld because the properties, as you can see, we have a lower carbon equivalent, so it's easier to weld. We have better properties, of course. Let's go now and try to mix all this together and talk about weldability. In weldability, at the end is what we want to is to weld the steels, to weld the steels avoiding cracking, to weld the steels not with a special process that we can done in a laboratory, but with process that can be done in workshops. They have to be more specialized, but normal workshops, I mean, with something we can do every day. We are going to talk a lot about the hard affected zone. We are going to talk about that quite a lot because it's where we will find a lot of difference between the thermomechanical steels and the quenchable temper steels, between 460 and between 960. One thing is that in the normal steels, we have used all the from before up to now, up to only 355. What we were mainly concerned was to avoid having in this hard affected zone, having, let's say, a too big increase of the hardness. The hardness of the hard affected zone is a measure of the type of structure we have in there. We will see, or at least you don't have to forget that this is the part that we have the big cycle. The cycle of temperatures affect mainly this part of the steel. If that cycle is very quick, we get to type of Martensita, okay? We get to a structure called Martensita, and we don't want that. At least before, up to now, we don't want it because it's very hard, and we can have problems. That was what everybody told you when, let's say, when we were younger. So, I mean, we have to avoid that increase of hardness in the hard affected zone. We were always concerned with this. That's why the reason of preheating, the reason of having a maximum time of temperature difference between 800 and 500. That's called T. I mean, no, I think we'll see it in a moment. Here we can see it. I mean, the time that takes the steel to go from 800 degrees to 500 degrees in the hard affected zone will completely define the maximum hardness we have in the hard affected zone. If we have this it's usually called it's usually called temperature 855. If we have a very short time, we will get to a very big hardness. It's what we call when you put the salt into the water, you have a very quick cooling of the material, and you have a very strong material, but it's brittle. Okay, we don't want that. But on the other side, you can see that, of course, if you go to a very long time, you get a very small hardness. As you know, hardness is also clearly a measure of the tensile strength of the material. So we could say that if we have a big hardness, we have a high strength material, but it's brittle. It's brittle. That's what we have always been trying to avoid in normal steel in 355. Okay. Okay. Once again, we must always take into account that in a welding process we have the raw material, base material, but we have mainly the hard affected zone. That's the place where all the different passes of the welding are acting in a cycle. Because if we do, for example, if we do preheating, we have a preheating temperature, we will make that the temperature goes down more slowly. So we will have a bigger time from 800 to 500. Here we can see the hardness in the hard affected zone of a structural steel. This would be a normal steel. We will see later that thermomechanical but above all the quenchable temper steel, the 690, are completely different from this. In a normal steel, we have so we have the hardness appropriate to the material we have. in the material, in the wall metal, we can choose the wall metal, of course, but here in the cycle, if we have a very small cycle, I mean, time from 800 to 500 is small, it means the cooling is very quick, we will get a higher hardness. And we are always, this is one of the things we are always trying to avoid in our steels, in our welding procedures. This is part of a qualification process of a welding. You know that one of the things we do is to do what we call barrier relatives. I mean, on a line parallel to the plate, 2 millimeters here, another 2 millimeters, so 1 in the middle, with 3 points here, 3 points here, 3 points here, 3 points here, okay. And here you can even see the values of the hardness. As you can see, in the material, it must be a 355 because the relation is 3.35. If you multiply 118 by 0.33, you get something like 500. That's the tensile strength of a 355. Okay, this is a 355. But here you can see 360. For example. Here, the hardness of the material is very, very high. This is the normal phase because in the weld metals, you can control it. In the middle, each layer you apply normalizes the steel that's already there. This is, I mean, if you do a radiography or ultrasonidos or anything, you won't detect that. But you have one thing that we call a hardness point. It's a very, and that's a big problem. Okay, that's what we have always talked about. This is the problem: is to have a hardness which because it's double. Here you have something that's more or less a 960, more than a 960. Okay, but this is a still. This has been the great concern of all our welding, the standards for welding, for controlling everything is always this. I mean, the control, the maximum hardness that we have. Because if we have this hardness, we have martensita. If we have martensita, and we have also for the first element of the tabla periodica, that's the hydrogeno. It's a problem for bolts. It's a problem for welding. If we also have hydrogen. Even from welding elements, we will have problems. We mix all these things, we can get to problems. Well, the general philosophy is this, okay? That's why this is, for example, taken from the American Welding Society. I think it's 1.5 from bridges. But that's why we start talking about the preheating temperature, because if we do preheating, we'll be able to control that very quick. We'll have the slower the time it takes from 800 to 500 would be bigger. I think this is very important for everybody to have this clear. And if we have a bigger time, we will not get this hard structure, this nartensita. We will not get to these high values. That's what some parts, even in this type of standards, give you talk about hardness control. It's another way of talking of the same things. We have to avoid this very quick cooling of the weld material. We have to avoid it. Of course, another word is hydrogen control, because well, I don't know, maybe from an university point of view, it's more understood, but we don't really. I think it's not really understood why. But I mean, there's a problem with hydrogen, and it's mixed with this hardness in the material will give us problem. We try to avoid it. How do we avoid the hydrogen? We can talk about anything. I mean, all these things have their practical point of view. we have to keep our electrodes. We have to keep all our electrodes. They have to be dry, not to have water. We have to keep our surfaces. If we want to have electrodes dry, we have to put them into ovens. I mean, if we have to take care of any of these things, we have to waste money, let's say, have to take more care. Okay. Of course, if we have a very easy material, you don't have to take care of anything. Okay. Here, for example, it's only to talk about something, but you can see that this is a quite big plate. But anyway, the difference between preheating and without preheating and with heating. I want to show you. These are the values that obtained in the two cases, without preheating and with preheating. You get up to values of 164 in the heat affected zone. Here, this is the reason of why. I mean, a workshop doesn't want to put preheating. It's a waste of money, a waste of time. People, it's not easy to weld because you cannot touch the plates. But you have to avoid having these high values in the heat affected zone. So we have to put preheating. This will go. The values, the number of values we accept is 350. Also 400. When we accept 350 or when we accept 400, it depends of the, I don't know in English, but the electrode, the content of hydrogen of the electrode. If it's a very low content, we can get up to 400. If it's higher content, we only can accept 350. And this type of things is what workshops should do. I mean, they should try with one temperature, with another temperature, with one electrodes. Okay, you may be thinking, what does this has to do with well, this is something more, let's say, more looks better, but at the end it's the same. It's the same. It gives us the hardness of a steel at P55, and we can see that we have in the heat affected zone. You know, where was the last welding game? You can see it because that's the weld that was not affected by the next welds. Because if you have a weld that's affected by the next welds, they improve, and that's where you have the. Well, we'll get back to this later, but I wanted to show you, for example, 460. This is a 460. 460. Let's say, is not a big transition. I mean, from 355 to 460, we can say that things are smooth. The change is smooth. We have better properties, toughness is better, not much difficult to weld them, and the problem is more or less the same. We have to avoid in the heat affected zone these very big values. Okay. Even the fabrication is done by a thermomechanical process. Well, not to be talking about, for example, we use 460 in this file. Of course, for using high strength steel, you have to have the opportunity. You have to look to a situation in which, first of all, you have to be able to use it. I mean, you have to avoid things like general bottling or very. I mean, this is a funicular curve, and all the materials under compression, more or less compression. So everything can be. We used it because we had a direction, for example. Direction you can. Well, the pipe will take is 350, of course, which is a normal deck, and on top of the deck. That's no question of using it on the deck. You can use it on the pylon because it's all under compression. It's a very small section. We even had the original design, or even had here, let's say, a second plate. A second plate here, we have two plates. So it was very difficult to weld all these connections on site because you had two plates. Using a high strength steel, we were able to put all the material on the outside, have only and we have an access from the inside and from outside, so we can be well welded with access from the two sides. And also, direction was made easier. I mean, these are normal things that everybody says about why do you use high strength steel, but you have to find a place where you can use it. You cannot use it anywhere. We use also the main the stiffness of the same place. We only ask for materials of 50, 30, 40, very small quantities of plates. This is some time ago. This is about I mean, well, these are, as you can see, of course, we can use the crane. We have water connection, as you saw before, because the connections were very bolted at the first moment, so the crane can do a lot of work, hasn't got to stop. But then at the outside, we do the welding of all the plates. All right, see, right? The plates are welded, but at the beginning, the only bolts are used for the operational connection. So we don't have to wait for the crane to monitor. Okay. But this is a very, I think it's a good case where you can use high strength steel, 460. Here I have another case. This is several railway bridges in Romania. It's a new European line, a double track European line. I think it's corridor number 7 or something like that. It's paid by the European Community, and they are, and we have, let's say, we have parts of 460. These are about 80 meters, 120, 80 meters. There are 7 bridges like this, and all in the same line. Okay, it's very good for the workshop. and 460 is the part that you see in red. Of course, what are the parts we use in a bridge in 460? Of course, the parts that don't affect. Another good system for another good place to use high strength steel is in a system in which the deflections is not a problem. Of course, you have then trusses a good place to use them. Even on top of the supports, you know, the famous sagging moment, there you can use 460 without affecting too much the deflections or anything like that. At the end, we use it a little bit on the middle, but mainly where we'll talk about. It's a very simple section. I'm happy with the section we use in this bridge. I don't know, it's not the object of these talks, but we use our section on top. It's the age, is normal age, but situation, but here is the other way. We were launching the bridge on this part, and the details were very simplified by this type of sections that we have used several times more. Okay. Of course, only 460 were used in this main course and in the places I have shown you before. And here we come to another. Of course, one of the problems is that you have to take a lot of care if you use 460 with bridges. Is with another typical problem is fatigue. Okay. Well, we didn't have fatigue problem in the pilot, of course. There was no fatigue problem in the pilot. Here we have, and so we have to, let's say, and we will talk about here about it, ways to improve the fatigue resistance. Because as you know, when you have welds, and the welding is the main process of fabrication, the fatigue detail is controlled by the fact that it's welded. So you don't improve too much. I'm trying to be clear saying all these words because this is not true for the steel itself. The steel itself has a different fatigue classification by itself, but it has to be unwelded. Okay, if we are welding, there's no difference between 460, 690, or whatever. So if we have to have something to improve. Here you see those small red lines, and our parts. Well, of course, we try to improve the details there. Of course, you can see all this detail, and not here, but in some places here, you see we have also applied some. It's called. We use the one called high fit frequency pin. I mean, we have used high fit for all these wells, okay, to improve their fatigue response. Now we are talking about the fatigue response of something that is welded. At some point, I hope we will get to improving the fatigue response of something that is bolted. Because once we have high strength steel, we have to understand that in all aspects, let's say bolted, welded, buckling, or anything, we are moving a little bit to the edge of what we at this moment understand, and we have to take more care about all these things. Of course, about these things are present in other steels, but in other steels it's not so important. Okay. Well, this is it's a photograph. Anyway, you are seeing that something has happened there to the walls. Okay. Here you're starting to see this is the short pinning where the high fit we have done all around these details, only in the parts that are really needed, because we are a precision company. We have to keep we have to know where it's really needed. Okay, it hasn't been easy. This is in Romania. To use 460 in Romania, I don't know if you have worked there, but the drawings, the contracts, the drawings are signed by 15 persons. I mean, it's all full of I mean, it's very, very difficult to make people change. Okay, yeah, we have to, but you always find something. We were in contact with some people in the University of Timisoara, and well, I think they understood. They saw that we really tried to care the details, because at the end, you know, steel structures are the details, and even more when we are using a very high strength steel, you have to take a lot more care in the details. All these bridges are completely welded, of course. Welded were done here in Spain, but then they were taken there, and everything is more generous. But remember, fatigue. Okay, we have to take care of fatigue if we have high strength steel. We have to avoid, of course, systems in which deflection can be a problem. So we have to use it in some parts of the structure. We have never done, for example, in the Bernabeu, we will finish at the end, we'll talk about the Bernabeu, we have more, you could say, 3,000 of 460, 3,000 of 690, and probably we have a little bit, the rest, a little bit more in the normal steels. Okay? A little bit more of this subject. Well, here there were only some photographs to make things a little bit advancing. Yeah. Another place it's good to use for high strength steel is in these yellow elements in the auxiliary structure. There nobody makes you questions, because we pay it. I mean, we are a construction company. We are using that, and it's very worthwhile to be lighting many times. We will see later in the Bernabeu, and we will mention a lot. I mean, and it's in a good place even in which you can do do tests, we could say, but no test, but a little bit more than test. I mean, you can use it on site in a real situation. Okay, guiding. Okay. This is not the object of this meeting. In the middle, that's always a good thing. Well, here I come back to the subject of the high feed. So you don't forget it. I mean, as you know, it's always a compression system. And we are using this system because it's easy to apply. I mean, it's quite easy to apply. This is I think we haven't used this one. It's the commercial one. I think it's from paper. It's a very simple thing. And even not doing it very well. I mean, even if someone that uses it is new, you get good results. I mean, that's important also because you cannot be confident that it's going to be done perfectly. I mean, things are never done perfectly. This has been quite a lot of tested in a lot of European programs, because now there's a program, I think, in Europe called something like Refresh, that comes from refreshing structures, because there are a lot of trusses, mainly trusses, that have reached their, let's say, their life. There are 100. I mean, remember many trusses that were made in the at the beginning of the 19th century have more than 100 years. There are bridges that have to be, let's say, that's why they call it refresh, and they are looking for systems in which to give them more life. They are mainly railway bridges, trusses used in all Europe, in Germany, and all that. I'm not going to talk about that, but that's why they have, let's say, stimulated all these systems to improve or to get better results in a new structure. These are results. You get very better results with this type of systems. One thing, at least, to mention about this is that these fatigue improvements depend on the yield strength. You get better improvement with a better steel. We will see that this happens many times, but many times this is not, let's say, there's not enough confidence, or it's not in the standards, it hasn't been written, or whatever you want. But many of the things we're going to talk improve with the yield strength of the material. So you get a much better improvement with this. Of course, as you can understand, everybody can understand, standards have to be cautious, let's say, or something like that. I mean, I don't know which word to use, but they have to be careful. But it's clear that that's what we have to go on. I understand we have to go on doing a lot of tests in universities or whatever. There have to be more tests of all these things. But it's clear that in high strength steels, we have to. It's a more expensive material, of course, and you have to be able to use it. Just before we were talking about, you have to, besides using a high strength steel, you have to use calculation methods, systems of calculation, more detailed, but to take advantage of the high-end steel. You cannot simply use high-strength steel to cover and then not to do anything else. I mean, that's why you have to mix it with other things. We always try to mix it with other things. Well, here you can see how the improvement gets difficult to one. You're seeing that how it's improving. It's improving with the material, with the material. Okay, it's improving with the material, the fatigue. So we don't have to forget that some up to now, with all of you or all of us, when you get to Euro code 1.9, I think, fatigue, no, there's no difference with the material. No different, no. The table is completely the same for any material. So that's what I mean when we get to high strength steel, many of the things that are more or less, we have always said that it was like this and that, but okay, it's a little bit not exactly that way. Okay, and we have to try to take possible advantage of all these situations. Okay. Well, this is the new stadium we are working on. Here we have, I think it's better in this one here. Here we have, this is, for example, this is this one. We want to talk about this one. This is one of the big transfer with the tension element here. And here I'm going to show you which parts are made of each steel. Up front. What you see, this is this color. This is 690. Or this, okay. And 460 is all around. Here, well, these are the only ones that are green is because it's in this element, all is nearly all 460 and 690. Here, these are the other ones, the ones that were in cross direction. In these ones, we have still some 460, but we don't have really no 690, and we have, at the end, you have to use it where it's worth. Okay, because you also have buckling, local buckling. You have to have a relation here. Here, the plates, for example, here. Well, one of the things, of course, you have to have some type of. Here we have in yellow. Well, it's not the colors we saw before, but these ones, the yellow ones are the ones that's at 690. The red ones are the ones that are 460. And here you don't see any ones that are green, but the ones that are green were. One of the problems is that you have to be very careful in the workshop because you have these things are let's say are not very technical, but it's a problem. You have to be you have to be very careful with when you're working with 3, 4, or well, because in the Bernabeu at the end you also have for 235 or secondary internet and all that. I'm not talking about that, but you already have it. You have at the end you may have a lot of steers. Well, these are the plates. The plates were very big plates. One of the things we also usually do when we use 460 or 690 is, and that's, and as I have told you before, and I will tell you later also, is anything in the world I think has, you have to pay for it. Anything. If you are using good material, you have to pay taking more care. If you are, one of the things we usually do with 460, 900, and 690 is we ask for them with approved yield strength. You can ask for that. It's a cost, a small cost, 25 euros a kilogram, or not too much. And you have up to, for example, here the place we're up to 65 millimeters. We have the 600 from 690. We have the whole use. You don't have, let's say, as in aero code or any standards or which is standard or a reduction with the thickness of the plate. Okay, because that's very sometimes it's a little bit when you start make a little bit plate a little bit bigger, then the plate gets lower. Then when you have buckling, it has gone up. You get into a circle. It's a good thing to ask them. Now it can be done. Okay, you're not going to do it for a building or normal building, but for something that you really consider it's important. You're using high strength steel. You can ask also to have approved yield strength or the properties independent up to some limit of the thickness. Okay. But here you can see some of the mainly here are 65 millimeters. All the connections will be welded. We will be bolted on site. Okay, that's another thing. Of course, we have not welded on site. Nothing. No 690 has been welded on site. not a single plate. Okay, we are saying it can be welded. We're going to go on talking about what we talked before. We're going back to what we talked before. But even if it can be done, it's clearly more cautious to do it always in the workshop. When you're using high strength steel, at least from 690 upwards, 690, you usually only weld it on the workshop. And I can tell you, I think at the end here in Spain, when we have at least no more than two workshops that can weld 690. And even those workshops, at the end, you can the persons that weld them are the 2 or 3, they are very special, or the machines. Okay, the machines or welding. Before getting into this subject of 690, for example, in the stadium, or I don't know, on the place we'll talk about later, one of the things is before getting into this subject, we asked for material to the company, to Gillinger. In this case, all the 690 was from Gillinger. We asked for this material. We done with 50 millimeters. We done a lot of tests. But that was even before trying to go to the job, trying to get the job. Because we have to be more or less confident that we can do it. Okay, because if the workshop is not used to do it, then you start having problems. I mean, it doesn't get the same quantity of steel for hours. It doesn't. I mean, it's difficult. He has to be trusted that he can do it in time. Okay? We're talking. This meeting is about 619, 460, but I mean, we don't use them all the days. I mean, we have only used them in some places. I think we have to be clear about this subject, and we only have used them with these workshops, with a lot of tests. All these subjects of the harness, we are also doing them on all the connections done. We are not only testing the procedure, but we're also doing some tests on all the welds. We'll try to go back, if possible, to this subject before, afterwards. But we test, let's say, non-destructive testing of all the welds. Well, we have talked about welding a little bit, not completely, but a lot. About bolting. About bolting, we could. I mean, you have to understand that, for example, I was talking before that there are whole books about high-strength steel. We cannot talk in one single hour about all these problems of high-strength steel. I only want to tell you at least some of the problems or things that we have to take advantage. In error code, up to some moment, we had the subject of the 0.9 when we have holes. Now it's allowed not to take into account the 0.9 when you are done, when you do the holes when you avoid making the holes, you avoid possible notches, of course, that's where you want to have the problem. So we can take that coefficient out. Again, I'm telling you, you have to take the 1.1 that I told you at the beginning. You have to try to use the 0.9. You have to try to take full advantage of the steel you have in your hands. Now I'm going to start a little bit about buckling. In buckling, here as I'm telling you, the main process of the structure are shapes with 65 millimeter flanges in 416, 690. All the edges of those plates have been flame cut. When you get to the specification, if you do the project, you have to do some drawings and you have to do the specification. You cannot separate one thing from the other. We also do the specification, and we ask for holes that are drilled, as I said before, or some other things that I had. And we ask that all the places that from which we are getting those elements for the cords have been flame cut. What are we looking for with this? As you may remember, it's clear that the selection of the buckling curves in Eurocode is due to the residual stresses. Okay, nobody says, it's not said anywhere, but it's clear. It's due to the distribution of the residual stresses in the cross section. And of course, the table, let's say, is limited because they cannot put a huge table. I mean, explaining all the cases. But in this subject of the H sections, there's a huge difference between having let's say the frames, the plates flame cut or not. As you know, I don't know if it's in another slide or not, but as you know, you have residual stresses, you have residual stresses, positive tension, you have tension when you have the welding, and if you have also a flame cut, there you also have tension. And I think it's clear, no? And then the rest of the section is in equilibrium, is in equilibrium between this compression and the tension you have. The normal situation. For example, in try to come back. I want you to understand this. It's very important. And in a rolling plate, in the edges, we have compression. Okay. In a flame cut plate, with a weld on a flame, if you do a welding, here you have the tension. Let's say, because before up to now, everybody said that this tension was the gears. Okay, more or less. Let's say it's that way by the moment. And then here is the compression. If you have a flame cut plate, you have tension on the edges. So this plate and this plate, as you can see, completely different. They are completely different. In Eurocode now, there's no difference between the buckling of an H section about the weak axis. The weak axis. There's no difference. We don't talk about flame cut, no flame cut, or roll, or nothing. If they don't talk about nothing, they are considering the worst. What I mean is that they are considering for the buckling of all those sections we have seen, we have used in the bridge also, because it's also an H section, or in the trusses of the stadium, also the same section. They're using always a curve. And as you know, the difference when you have small slenderness, the difference in the curves are very big. Very big. Here, the difference between having one curve or another one. So when you have small slenderness, that's where we are using here. We are using here. You're using ISISE, you have to avoid having a very technical buckling. So we are working here. So it's very important, the selection of the curve. Here I have written, I have written that the buckling about the, I think so code normally calls the small axis, is critical. It's critical. And there's a very big difference. We are saying that the difference is 8% or 12%. Another 10%. We have talked about several 10%. If you have a reduction with thickness of the yield strength, you have more than a 10%. If you have to consider the high consequences of failure, you have to consider 1.1. If you have to consider this, you have 1.1, 1.1, 1.1, 1.1, you get to 1.30. Okay, you are not using the material. So what we ask for is to have this place in to have, well, here you have another drawing. This is very old. This is very old. This figure is very old, but it has been, let's say, taken away from the Eurocode. This figure gives you the distribution of residual stresses in where the shape back in which the plates are rolled or straight cut. Okay. Compression, and here tension, as we are. The bottom is around this subject. Of course, that's why the worst thing is to have, of course, compression, residual stress compression in the place where I want to have the bottom. That's obvious. Well, this, of course, I think there are. This is a this was done in old Euro codes. This is something from a very old Euro code. Don't know of one data. It was a very an old thing that was taken away, and now when that has been good for us, because now when we have to tell the, let's say, the engineers of the client, we want to use a better curve. Well, why I want to use this better curve? Well, this is nothing new. This is nothing new over the planet. This was proved a lot of years ago, and never could even consider it. The question is that it has been taken away. It has been taken away because to make more things, let's say, more simple, more easy, no? Because I think we were talking about this a moment ago, that Euro code, everybody has to use Euro code, or everybody that finishes has to use it, and you have to be careful, because if you're going to use things, you have to understand a little bit more. One of things, well, there's a. Up to now, up to let's say up to recently, everybody said that the residual distribution of residual stresses was independent of the use. Was independent. They always said, as you know, for example, when you have to model by element for calculations, you have the distribution of residual stresses. The residual stresses is a fraction of the yield point. That way, you are saying that they are related to the yield point. It's not. It has more or less. It's doing the studies, but it's not that way. The distribution of residual stresses in a high strength steel, they are less residual stresses. So we are getting to the point. Of course, all these things have to be more crude, whatever you want to see, okay? But this is going to improve the curve we have. Not only what I told you before, that was cutting edges, that's the distribution, but even taking into account the yield strength of the material, we have an improvement in the booking stress. Well, this is here you can see it. That according to Euro actually here, and it is completely over the best curve. Are completely over the best curve. Okay. Well, we haven't used this, okay, because you can now not use everything you see, because okay, things have to be more crude and more. We haven't used this, okay, but I think it's also even there are even studies in which you already have formulation, analytical formulation, in which you modify the factors that are related to the curve. You modify them according to the yield point, and you get a better adjustment. Okay, but there are a lot of articles about those things. They've been made. There's some standards. Okay. Euro code is started to do that. If you remember, many parts of Euro code you have a better with 460. You have, and now you have a column with 460. In the famous table, instead of selection of the, you have a table with 460, but they haven't gone. Well, they haven't gone to 619 to 960. They haven't tried still, I think they maybe get there some portion, but they haven't gone there. They have, okay, 260. Well, I'll try to go as quickly as possible. And I'll have to go back where we started about with this famous time between 500 degrees, and 800 degrees and 500 degrees. As you can see, I'll try, let's see. That's how it's normally for the 845 time in upper values. What we have to start to have clear is that with a very high strength steel, now we are going to start talking mainly about 690 and the, let's say, possible use, we haven't used it still, and less as welded of 960, okay? Up to now, we have, in all those things we talk about welding, we have tried to avoid this very high hardness in the hard affected zone. So we have to control the heating to have at least some type of a minimum size of the welds, heating temperature, and everything is to try to have a very short, a very quick load to get there of the temperature that can give us this structure that we don't want. So we have a limit from under now, from the under. Now, with the high strength steel, we will find that we have another limit that comes from the upper part. So what we are saying is that when we have high strength steel, we have an upper limit and a lower limit, and they are getting, as we get higher and higher, they get closer. So it's more complicated to do the welding. Okay, in normal steels, 355, 200, we only have to be worried about not doing things very quickly. We're having a very low limit from the bottom. Now we are going to start to have a limit from the top. The difference is, as we mentioned, that that all these high strength steel, the 690, 960, they are made, as that's why I started with when we started at the beginning. They are made from quenched and tempered steels. They are made, the main properties are gained by the temperature, the control of temperature. So now, let's say, this is what some people call the welding box. The welding box is that you are getting this welding box for each material. If we have, I don't know if we have one for 960. If we have one for 960, this will get closer and closer. So we are getting, and even if you imagine a better one, you're getting, it's very, very critical. Everything is critical. It's critical to do the welding very quick and very slow, because one way of controlling the temperature of the weld is the speed of the movement of the electrode, the heat input. No, to control the heat input, you cannot have a very quick one, not a very small, slow one. Well, this is well, I don't know if you are doing this, but this is supposed to not, you haven't seen it, because this is a the Finnish comments, the Finnish from Finland, from Finland, the comments to Eurocode 1.12. Okay, as you know, I don't really understand it, because as you know, people from Norway, Sweden, and all that have always been the ones that have proposed pushed the use of high strength steel. Well, but now they write something like this. I'll tell you more or less the important thing is that there's a reduction in the strength in hard affected zone. There is a reduction in the strength of hard affected zone. In high strength steel, what we are talking now about 690, okay? 690, 960. We have said that 460 was with the other steels, more or less, okay? What they are trying to say, and that's the main concern, is that In the hard affected zone, instead of having these things that we saw before, that the hardness went up and we went to 400 and 360, we go down. We go down. So we lose strength in the hard affected zone. But okay, the Finnish people, but if you see here, this amount of heat input levels too. 85 seconds. 85 seconds. I don't know if you remember. I don't know where I had it. But I don't know. Well, I don't know. I hope I will get to that. But remember that we were talking about 10 seconds or 20 seconds. What they have done to get those results is that they have done the welding very slow. I mean, and so they have the temperature has slowed very. They have not getting a functional temperature still. That's why they have got to dose. Of course, there has to be, as I told you, a concern about this limit. But if you do the things well, that's not the problem. Okay. But anyway, I wanted to tell you that there are people that are saying, be careful. In Eurocode 12, Eurocode's high sensitivity Eurocode, you have to be careful because there is no, what they just finished people are saying is that in Eurocode 1.12, nobody is saying that you have to be careful because you can have a loss of strength in the hard affected zone. That's what they are saying. And it's true, you can have it. But I think we have to go to work from the beginning with something that's more singular, more special, like high strength steel. You have to be more careful. You cannot do in a workshop, be welding. It's now break time. It's break time. You stop. No, no, you cannot do it. Maybe you can do it with 355, but you cannot do it with this. Here you have one. Okay, the Finnish people, the same. You see that it breaks in the heat affects. Doesn't break here, or doesn't break here. Okay, but that's clear. If you do a welding procedure, they break or the coupon or the test have to break in the have to break there. This is it's a little bit simplified, but you have to as soon as you see this and this, even if you can see that this is the as I showed you the other thing before, now I have to show you that you can get this the blue one. I mean, here you have to be able to see that you can have in the heat affected zone is where you can have less resistance, less hardness. It's completely on the other way. What we saw for 355 and more or less can be for 460 is completely different for 690, and we talk about 960. But from my point of view, we haven't welded to 960. Okay, so what I tell you about welding is for 690. It's this one. With 960, you can find a lot of literature or articles in the internet of problems they have. The 960 they use it for cranes, and they still have problems. They still have problems. They find problems, a lot of problems. This is the certificates from Dillinger, which you can see that we get easily 65 plates all the tension I mentioned to you. And this is I'm trying to show you now here. Okay, it's a little slightly smaller than here. the values in the heat affected zone instead of what we saw at the beginning, that we were getting to very big values here. Now we can even have a slightly smaller value than in the dry material. These are real tests. Okay, these are tests we have done. Okay. Of course, we haven't. If you wait for 85 seconds, these are normal times. Anyway, I'm not going to talk about that, but there are. If you look to articles, there are now some studying things. The loss of strength in the hard affected zone also depends on the size of the hard affected zone. I mean, if you have a very small part that has lost its resistance, let's say, the general resistance, you won't notice it. It's a little bit surprising, but it works like that. Okay, people are studying that. But anyway, what I wanted to tell you is here. Here you see this 400 to 448. See this. But what this, as you see, some figures of photographs of these trusses. I'll go quickly. These are 120 millimeter plates in 460. These are plates in 460 also. As you can see here, some details. 460. Some plates are in 690 for connections. This is a full tri-direction on site. This is a full tri-direction on site. Before direction on and well, this is only an example of some article that you can see in which you still find cracking in 960. I won't be able to talk about another aspect that's very important, that is how water connections in high strength steel work. Fortunately, I think there are starting to be some studies about this. I told you some Chinese people that I don't know, they have a lot of time to do a lot of tests, and they have done. But we have to be. But at the beginning, you don't have the confidence. You have to do the water connections in 690. Follow more or less have enough dutability to be more or less similar and to allow the calculations we are using in Eurocode up to now? The answer is yes. I will try to be more studies about the subject, but this has to also to be proved, let's say, okay? This is a proposal we are doing in another study to replace some cables with 960. These cables, these elements of 960. I don't know if you have seen that many cranes. They have changed the cables here, high-strength cables. They have changed them by plates. These plates are mainly 960 now. Well, I cannot, the time is short. I only wanted to tell you this, that as I mentioned before, if we have something in 960 and we have to improve the fatigue, we also have systems to improve the fatigue in the halls. So we have systems to improve the fatigue in the walls, and we have systems to improve the fatigue in the halls. So there are solutions, for example. We only improve the fatigue in these small halls. We put them here. It's only to save money, okay? But if you, at the beginning, it costs money. This is the system that you people from airplanes have been using it from a long time. Okay, you know, it's all lot of rivets, and the critical ones they use this type of systems. I cannot explain it. Okay, that's it. Okay.
Very much. Questions? If there are any questions, I'll start. We have been involved in a project on opti-green European projects, where we tried to establish the advantages of using ice-strength steel for bridges, for plate girder composite bridges. And there was a lot of experimental testings. They were not done here, they were done in Stuttgart by Ulrike Pullman. And she compared the behavior, the fatigue behavior with and without hammer pinion. Yeah. So high frequency treatment. Of course, the improvements were significant. But there was also the issue that over time there is a loss of the efficiency of the hammer treatment. So this is something that
you have to, I mean, as far as what I see from the construction point of view of a company, you have to use all the things, but with care, because there are a lot of things that are still not so well tested, so much tested. Of course, it's something you always have to use it. Many times we use it to prove the client that we are taking care, that we are trying to do something a little bit done, but we don't have to take it into account in the final life. So that's the thing. But if the client can see it many times, because if he sees that, I won't mention, but in these 7 bridges, some bridges were from us and some bridges were from another company. If someone shows something in which he's trying to take care, from a technical point of view, I mean, and the other person doesn't show anything, I think it makes a big difference. That's why we don't even are not afraid of using systems that are a little bit more expensive or anything. I think it's interesting. And in these all auxiliary structures we have made, we have already also tested this quite well.
So because in fact, in this case, then I mean, as a final comparison, there was an application to several to designing in S460, design in 690, and then in what it was called improved design with 690, taking advantage of the high frequency tuning and some changes in the design rules of Part 1.5 of Eurocode that in fact will be part of the new version now, but they were used for the comparison, and this showed that the design, this design would be cheaper and in a life cycle perspective better than using 460, for example.
I didn't talk about that, but for example, in this group, for example, we even have in the top we have a retractable group. Okay, in that group we even have some composites, because that's another reason for using some different high strength steel. If you are using somewhere where the savings in weight affect everything that's go up, down, 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 you get a lot of savings. If you have that truss, simply that truss was in a bridge, the savings would be smaller than there, because there they are using upwards, they are saving money down, 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 a lot of money going down. You have to look at some places to use it, because we do have with 690. What I have seen is that we have suppliers, as number of suppliers. you have a delivery time. Delivery time is worse. It's worse. You have, and you know, the construction company, well, you know how we are in Portugal and Spain. You know, you quickly go, quickly go down. So I mean, you have to be sure where you to use. Has to be with advantages. But we have with 690 here and with 460, we have got advantages, big advantages.
Questions?
In the roof of the Real Madrid, those advantages, those economical advantages, can you say it was 10%, 15%?
I think it was more. It's difficult to say because at the end you never make the whole design put it that way. But when you start doing it, this thing that I'm telling you that as soon as, because for example in a stadium, imagine the stadium is quite heavy. I mean the self-weight is very big a component compared with wind, snow, and all that. So if you say there, if you start the wheel, you start the famous wheel, you go down, 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 and it's worth the pity. It's really worth it.
But the original design was with another kind of steel, or
No, the original design was completely different. And that's why I'm telling you also this subject of the 1.1 or the 0.9 or the buckling and all that, because I think you have to go into that wheel of improving everything, so everything can. Once you ask for a delivery time of 690, you can ask for approved year step. The money is the quantity is very small, but with 65 millimeters, according to Euro code, you have a reduction. You don't have a reduction. That's problem. One. But so with 690 and with 960, there is a difference between the suppliers. Not all the steel, not all 660, 90, and all the 960 is the same. I cannot talk about all because I don't know about all, but we have at least one that we will never ask for, and we are buying it from dealing there or from this other one, another German one that I showed there, of course, but for example, normally now they call strengths, no? Strengths. Before it was, oh, it was now it's strengths. But with other ones, be careful. Not the same. We have steel, we have welded, and all these values were completely different. And you learn more when you have problems like this one than when you have everything goes well. Because when you see that there's a huge problem, you say, okay.
Any more? Okay, so thank you very much.